Welcome, everyone. We're going to make another attempt at introducing this topic of uh, measuring the volume of solids by slicing them into cross sections. If I could start over again here, this process starts with recognizing that these solids are going to have a common cross section, all sitting in a region that we draw on our coordinate plane. So it usually starts with two or more equations of functions. And it starts in the two-dimensional coordinate plane, and then as we move it, we'll be able to see the object in 3 dimensions. What I've got on the screen now is a graph of two functions along with two vertical lines, both drawn in the XY plane. And right now, the equations of these curves is not super important, but there's like a sine or trigonometric function up here, and then there's just a standard sloped line under it. And then there's two vertical lines. This is supposed to be at x equals -7. This one's at x equals 8. And what we're going to do now is we're going to rotate this in 3 dimensions so that the xy plane ends up kind of being flat on the ground, so to speak. And our solid is one that if I slice through the xy plane perpendicular to the x-axis, notice that's the slice is happening right here. In fact, as I move it across, then coming out of the xy plane is a square cross section. And so because it's a square, it is just as tall as it is the distance across between the two curves. And so as we go across, if the distance between the curves is bigger, the squares get bigger. And if the distance is smaller, the squares get smaller. And each of those squares has a little bit of thickness to it. And so if you want to think of those then as a little slice whose area is the area of the square, and then whose thickness might be a small, tiny little bit, like even a fraction of an inch, then the volume of that slice would be the area of that particular square times the thickness. And what calculus or integration is going to do is quickly add all those volumes together as I move across the x number line from, in this case, from -7 all the way through here to 8. Okay, so the process of summing up or adding up all those little volumes is what integration does. And so what I'd like to try and do is break this process down, like solving a typical problem, into just a couple of small steps here. The main emphasis today is taking what information is given to you and constructing the definite integral. Of course, we would want to be able to solve the definite integral to know the actual volume, but what most students have trouble with is even just setting up the definite integral from scratch. Okay, so I'm actually going to pull up my example here, and we'll try and walk through the process first of setting this up. So in class the other day, I talked about some of the more common cross sections that we're going to encounter in this unit, such as squares, where if you know the distance along one edge, squaring that gives you the area of the square. An equilateral triangle, where if I know the edge length of the equilateral triangle, we kind of figured out that side length squared times radical 3/4 gives the area of that. And here's a semicircle, and if I know what the diameter is, then pi/8 times the diameter squared gives the area of that. Another common shape is a rectangle where one length varies depending on the slicing of the region, and then maybe the height will be something constant like 3, or we might encounter one where the height is mentioned in relation to its length compared to the width. Okay, so if I could break starting a problem off from scratch, usually given to you will be the equations used to define the base region. Quite often, those are just either two intersecting curves or functions, or they might be two non-intersecting functions along with some vertical lines. Let's just suppose it was two functions that intersect. So maybe there's a curve here, we'll call that f, function f of x, and maybe there's another function g of x coming along down here. and we're gonna just call this intersection point A, this intersection point B. And then it says, usually it'll say that region is going to be the base of a solid, and then it's going to tell you what direction to make your slices. You're either going to make the slices perpendicular to the x-axis, which would mean the slices in this picture will be vertical. And so if I do that, slicing perpendicular to the x-axis means a typical slice is right about there. And because we're going to be making volumes, let's make a tiny little rectangle here. But that is your slice. And so we want to know what that distance is. So what I call the typical distance across the region is just, how do I actually name that distance right there and describe it? Well, that distance will change depending on what value of x between A and B we're making the slice. So that distance there is going to be a function of x itself. Now I just call that distance s because it's going to be the side length of our squares, or the side length of our equilateral triangles, or it might be the diameter of our semicircles. But most commonly then, if we're slicing perpendicular to the x-axis and there is a clear upper function and lower function, that distance is going to be just the difference between those two functions. And I typically just call that s. And so we now use that in the same way we did in these geometry formulas to formulate what the area of a cross-section is. If I had square cross-sections, then coming out of this page toward us would be a square whose length and width are both that s. Okay, so the area of the volume of that slice is the area of that cross section, and again, that will depend, how we write that will depend on what the shape is, and then times the thickness of the slice, which is the delta x. And so integration is going to add up all those slices. Now, the other situation is maybe I'm going to slice perpendicular to the y-axis, and so what needs to happen then is your equations are going to have to be written as functions of y. And so they might graph like this. And so maybe this function is x equals f of y. And maybe this one over here is x equals g of y. So now your slices that run perpendicular to the y-axis are actually going to go like this. But once again, the curve that has the largest x value will be your upper function. The curve that has the lower x value is the lower function. And that distance, that typical distance there, is still going to be our side length of our slice. And I would probably say it's going to be f of y minus g of y in this particular case. And so then the area of the cross section is going to be a function of y. In either case, I need to know where the region starts and finishes. In this case, it's on the y-axis. And so in either case, multiplying the area formula for the cross-section times the thickness, delta x or dx, and then integrating across the region, either along the x-axis from A to B or along the y-axis from C to D, is going to give you the area, it's going to give you the volume of the region.